All right. Don't forget the course entry assignment. Yada, yada, yada. I guess I've taught 3 of you. I haven't had you in class before, have I? Okay. Figured we'd do class today, but unless there's a groundswell to want to do the lab, we'll do that by on Wednesday. Well, good news is that because we're gonna do it on Wednesday, the 152 class will be the first guinea pigs on the lab. All right, let's do a pre-course assignment or a pre-course assessment. So, you need, please do not write on this. Do not assume that any marks on it are indications of correct or incorrect. You need a separate sheet of paper and a pencil or pen, whatever. If you need paper, there's paper right here. When you're done, just bring it up. Do not wait for me to call them.
Is it for a grade?
Today is not for a grade, no. Need separate writing on paper.
You can't use yours on that.
For how are you going to submit that?
I was just checking the course entries.
Oh, you don't need the course entries. For right now, just work on this. Do you need paper?
Yes.
There you go. All right, for those who don't know me, I'm Dr. George Fox. Contact information is in the syllabus. My office is, you walk down the hall, first right, and then the first door you run into. It cleverly has my name on it, or right beside it. All right, Physics 252. We'll start out with, what is charge? And go.
Directional force.
What's a non-directional force? Force is the vector, therefore it will have a direction. Or, but that probably should be more specific, electric charge. Although within the context of this course, charge, I don't think we ever have charge meaning anything other than electric charge. All right. What do you know about electric charge?
There's a positive and a negative.
Okay. Is that it?
Neutral charge.
Okay. Is there another one? Not that anyone's found. Sorry, spoiler. Okay. What do you know about positive charges? Anything about them?
They don't attract other positives.
Okay. They just ignore each other.
They attract negatives, but ignore positives.
All right. So negatives and positives attract.
Yeah.
What about positive? Positive?
Nope. They repel.
Okay. More specifically.
Yeah.
What about negative? Negative.
No.
So something to keep in mind. Opposites attract. Like repels. What about -0?
It'll become a negative.
The 0 will become a negative?
Yeah.
Why?
Because the negativity of the charge would overtake the neutral.
I feel like there's some extra conditions in there that you've left off. So for example, I grabbed this part, I didn't grab the electroscope. I'll let you contemplate what happens with a -0 or +0 if you prefer. So I'm gonna leave that running, and I will grab an electroscope, and I know where they are. All right, and electroscope. Take some PVC, rabbit fur. If you're concerned about the rabbits all moved to the tropics. They don't need the fur anymore, so they donated them to science. The rabbits are fine. All right. What I'm doing as I'm rubbing these together is basically I'm making the PVC negatively charged. That is neutral. It seems to be reacting, but it's not negatively charged anymore. It actually was never negatively charged. Sometimes the leaves there get stuck. All right, so they react and then they go back. Okay, still working. So negative and 0?
The negative surrounds the neutral, the outside.
Oh, the negative charge from that surrounded it? Is that what you said? Is it easier to see without the glass there? I'm assuming everyone can see it.
Yeah.
PJ, that was a little less convincing. Can you see it?
I've already seen it before. So.
Okay. Theater of the mind. All right, sorry, Chris?
Yes.
Good, okay. Say it again.
The neutral charge if the negative's introduced to the neutral will be surrounded by the negative. But it won't change the inside.
But there was a reaction there. I'm not sure how that fits into your scheme. Anyone want to help him out or just leave him hanging there for a moment? Looks like they're leaving you hanging. All right, what else do we know? So apparently there's something going on there. Now, to Sarah?
Yes.
Sarah's point. I mean, I can make that negatively charged. Now it's negatively charged. I think sort of along the lines of what you were saying, but I've neutralized it. All right, so let's think about what's going on there. Why is it that when I brought a negatively charged thing towards it, the leaves went out a little bit, and when I touched it, they went out farther, and then they stayed apart until I neutralized it?
When you held it over, I don't know exactly, they might have gone into the leaves and the negative charges would have,
What went into the leaves?
the negative charge,
From where?
the pipe.
No.
Oh, can I take a guess?
Go for it.
There should be like a force field, right? Like, you know what I'm talking about?
The force field is probably not the right word, but there's a field, you're talking about an electric field?
Yeah, something like that.
Okay. Jumping ahead a couple chapters, but go for it.
I'm gonna assume that there is no force field when it comes to the thing, right? But then when it interacts with the PVC pipe, the force field stays with the thing.
They with the thing? That's what I heard. My hearing's not great, but
Like it stayed with the thing.
it stayed with the thing.
Yes.
Okay, so that's when I touched it. What about when I didn't touch it? Before I touched it, the leaves still moved apart. All right, let's drop back to a little bit of information here. What do we know is positively charged?
Protons.
Okay. What's negatively charged?
Electrons.
What's neutral? Among many other things. Which one is the most massive, or the least massive of the three?
Electron.
Yeah. So this is the smallest mass. What about protons and neutrons? What can you tell me about their mass?
Same size of
Roughly, it's probably size isn't the right word, but roughly the same amount of mass. If you get far enough into physics, you start looking at the differences there, but for what we're concerned, close enough. So if electrons are the smallest, if I apply a force of any type to an atom, let's make it an electric force. I apply an electric force to an atom, what's going to be most likely to move?
The electron.
Yeah, it's the smallest mass, it'll have the greatest acceleration. So the other rule to keep in mind whenever I do any of these all right, so if I want to move protons, I basically have to move the whole thing. I'm about to move protons on the table here. There we go. I moved the protons, moved everything. But if the protons are moving in here, they're not shifting really relative space. They're, the leaves move, and so you could make an argument protons move, but we're not having protons move from the top to the bottom or bottom to the top, despite what some students have claimed in the past. So, taking that second rule into account, I bring a negatively charged pipe near the top of it, what's going to happen? No, not touching, no spark.
The electric field makes the electrons move down away from the pipe.
Okay, a true statement. Let's try to stay away from field for now. So the electric, they're repelled. So say it again. Once you said field,
It
my mind went off.
pushes the electrons down the leaves away from the pipe,
Okay, and so now the leaves are,
negatively charged,
and the knob,
positively.
I would think so. The whole thing still is neutral. We haven't added any charge yet. So when the leaves are both negatively charged, what would you expect to happen?
repel.
Yeah, and so thus they come apart. Now, I'm going to touch it, and the leaves should go apart. And they do. Now, and you can feel that. Less there, more there. All right, so the leaves are still apart. That means that they're either stuck, and sometimes they do get stuck, or it means that they are still charged of, in our case right here, negative. And I just touched it. So let's do it a little bit differently. Does this part a little bit more than before? Why does rubbing it make a difference? what? Surface area of the knob?
Or the pipe.
Why would that make a difference?
Well, if they're evenly spread across, then maybe it could. Wording, probably not right, but it could move the more electrons.
Why would rubbing this across there move more electrons? How about when I just touch it, why wouldn't the electrons just go, ooh, we got a positive knob here, let's go to it.
You mean all of the electrons in the pipe?
Yeah. Why would they not automatically just go,
With distance?
pardon?
With distance or the radius, like away from the knob, would that have anything to do with it?
We're assuming that I've touched it. Well, it depends on what you mean by that.
The distance from, let's say, the end of the PVC pipe to the knob versus the knob to the part that's touching it. Would that have any difference with the charges?
All right, so when you're saying that, so when I touch it here, the fact that that's a bigger distance,
Yeah.
why, okay, that has something to do with it, so why are those electrons not gonna just come over here and into the, it looks like I neutralized it. Why would the electrons just not go?
I guess it doesn't have enough force pulling them.
Why does it didn't have need much force for those leaves to go apart? What's the difference between this and this?
And the molecular, they're compounds.
No, not compound, but. I guess material science probably could connect it, but that's not where I'm going. Why do people working on electronics generally have rubber mats underneath them?
Insulation.
Is this an insulator or a conductor?
Insulation.
Electric conductor, obviously it's a pipe, fluids would go through it.
Insulator.
BJ?
Insulator.
And the shaft here?
So is it metal?
It is.
Conductor.
Yeah. So another key thing here is that for an insulator, charges cannot move particularly well. Ideally, they wouldn't move at all. So when I touch it right here, only the localized electrons would actually be able to move off of it. So by rubbing it, I'm allowing more electrons to move from here onto there. So it still goes back to what is electric charge? We're talking like, yeah, of course, we got electrons, which are negatively charged, protons positively charged, neutrons neutral, lots of other things, light is neutral. But we haven't really answered what electric charge is. And I'm gonna spoil part of that, is that we don't really know. There seems to be this property of materials such that there seem to be three types. Some attract, some repel. We can start narrowing it down, and there just seems to be this property which contains these things, and they had put a word on it, they call it charge. Right here. A physical property of matter which causes it to experience a force when it's near other electrically charged matter. That's vague. All right. Now, if I want to represent charge, of course, I will use the letter Q. I suspect it comes from somebody first talked about a quantity of something. Also, the symbol used for heat flow, or heat, I think flow is implied. Typically, that is for a single charge. And this is for a collection of charges. It seems to be a 99% rule. There are some gray areas where it becomes a little bit muddled, but it's a common thing in physics, because lowercase p is the momentum of a single object, largecase p is the total momentum. I will use them, I will go back and forth interchangeably. So if you're a purist and object to that, then just prepare yourself. All right. But I know what you're all thinking. You're thinking, this is great, but where's the math? So obviously, if objects are being moved, if we are taking an object and it is going from relatively at rest to being moved down to there, has to go from velocity of 0 to something, and therefore it is accelerating, therefore there must be a force applied. The electric force. And now is the reason why I don't use E for elastic force. And I also present to you the fourth physics equation of the two courses. First equation, F equals ma. Next equation, F equals big G m1 m2 over r squared. And the third equation of physics 151 was Planck's law, F equals negative k delta x. This will be the fourth physics equation. Everything else is just math and definitions. This will be the force on one from charge 2, so this is the force on charge 1 from charge 2. Now I know from Newton's third law, I should be able to switch objects and the magnitude of the force stays the same. So if I have two charges, if I flip positions, the magnitude of the force stays the same. So there must be some commutative property